going to talk about chemical bonding. And we are, of course. So we will start off by talking about our learning goals for this week. Now this is really throughout this entire chapter, but this is what we're going to start with this week. And you should get through all of these by the end of this week. It really kind of bleeds over into next week. It's from last week, but we didn't get where I thought we would last week. So by the end of this week for sure, and probably by the end of today, you'll be able to describe the differences between ionic and covalent bonding. You're going to be able to differentiate. There are actually different kinds of covalent bonds. You may not have known that. And you're going to be able to explain why any two given things bond the way they do. The other thing you're going to be able to do is look at any two elements and say, oh, those are going to form this kind of bond. You'll be able to do prediction on this. And we'll also start to talk today about how we get energy out of bonds. So that's the other thing that you'll be able to describe, which isn't covered there yet. Okay, so let's go to your what do you know, shall we? So we've got our learning goals, and these are actually from last week, but they're flowing into this week, and we'll have a few more as we go. The thing that you should know, that you probably know from physical science, is this. Two types of bonds, right? Ionic and covalent. And this is really what we cover in physical science. I am going to tell you that it was embarrassingly late in my life through a year of high school chemistry, through a bachelor's degree in biology with a minor in chemistry, and into my first year of teaching chemistry, that I could accurately remember which of these was which. Because nobody ever gave me a helpful mnemonic for it. Apparently I didn't care enough to figure one out on my own then. So ionic bonds are bonds of attraction between two ions. I know it's so easy that your third grade cousin could tell you this, but I didn't have it somehow. It just wasn't all connected upstairs. So yeah, if you have an ionic bond, you have two ions that are attracted to one another. That's all it is. It's very simple. And so we've got a little positive ion and a little negative ion, and they have a force of attraction between them, and because of that force of attraction, they stand shoulder to shoulder. They don't overlap, they don't become one thing. They're just standing shoulder to shoulder because they're powerfully attracted to one another. I mean, they're held shoulder to shoulder. But they are not connected in the way we think of things merging into one new thing. They're just standing shoulder to shoulder. Very attracted, very powerful bonds of attraction. And when we have an ionic substance, a substance that's held together with ionic bonds, we have huge numbers of positive and negative ions that are all standing shoulder to shoulder. So they tend to be really well put together. They tend to not come apart easily because you've got overwhelming numbers of things attracted to one another. But they're not really holding hands. They're just standing shoulder to shoulder. So if we go back to our old electron cloud metaphor of the little positive tennis ball of the nucleus surrounded by, a couple of meters of negative electron cloud cotton candy. Remember that? Our big fluffy cotton candy of electron cloud. In these two, the electron clouds are, they're right there, but there's no interweaving of the cotton candy. It's still two distinct electron clouds. Now, how many of you have ever been involved in a sport? Or watched a sport? Okay. Anybody ever been in a situation where you have a team captain? Okay. Does it ever happen that there are two team captains? What do they call them? Co-captains. You don't say. Co-captains. So let's do a little bit of sort of vocabulary breakdown. If we look at this word, I see V-A-L in there. V-A-L-E even. I could include the E. You seen that word recently or anything that's got that chunk in it? Valence. Valence electrons. Well, in covalent bonding, what we have are two atoms that are co-captains of the valence electron team. They are sharing their electrons, just as co-captains share their responsibilities. So in this case, these things are actually mingling their electron clouds. So rather than two distinct clouds, we now have something that looks more like this. So if we imagine our tennis balls surrounded by cotton candy, we've now woven the edges of that cotton candy cloud together. So they are holding hands, they are sharing orbitals. And the orbitals, the electrons from over here in this cloud, the valence electrons, are free to travel over into the electron cloud for that atom. So they actually, their outer energy levels are overlapping. And so electrons are flowing between the two of them. They are literally sharing them. Those electrons, it's like, well, years ago I knew somebody who took two mobile homes, shoved them up a very narrow driveway, cut a hole in one and welded them together. That's covalent bonding. They were absolutely sharing space. This is the level of understanding that you probably had coming out of physical science. Yes? Would you agree? So you can describe the difference at this point between the two forms of bonding. Pretty simple. And by now you've learned that every time I say, okay, that's pretty simple and that's what you should have known coming out of physical science, what's going to happen? We're going to make it more complicated. Yeah. So we oversimplify it to teach it to you in physical science. It is more complicated than that. So it's not really just covalent or ionic. Very few bonds are actually purely ionic or purely covalent. There is a spectrum of bonding. And you may or may not know what a spectrum is. The rainbow is a spectrum. You can have a spectrum of color. You can have a spectrum of maturity. You can have a spectrum of like or dislike for something. So it's a continuum where it's not yes or no, it's how strongly you fall. The political spectrum is a good one, and I think in Mrs. Moultrie's room they were attempting to paint the political spectrum, from people who fall on the very, very far right to the very, very far left, and people who are somewhere in the middle. That's a spectrum or continuum. And bonding is the same kind of thing. So, from totally ionic, where one atom is completely giving up its electrons, the other one is completely taking them, they are not sharing them, to purely covalent, where they are sharing them perfectly 100% evenly. The thing that makes a difference in that is how strongly how much each atom wants those electrons. If we think back to our sharing the covers metaphor, if you have ever spent a summer weekend at grandma's where you and 4 other cousins get thrown into a queen-size bed with one blanket, maybe you haven't had this delight, but you got a bunch of similar aged cousins, or you got a bunch of siblings, and you've ever been tossed into one big bed with one blanket. Not everybody shares evenly. It just doesn't happen. You always got cousin Joey, who wraps the blanket tightly around himself and then executes the rollover maneuver. And so he's got all the blankets wrapped around him, and you are shivering in your little t-shirt and shorts out there with no blanket on a nice chilly autumn night. What do we call that attraction of an atom for electrons? How strongly they pull the electrons to themselves when they're bonded to something else. It is an attraction, but what do we call that specifically? Yes, it is. Nobody in the other class caught that it was up there. I don't know if you guys did or not. Yeah, it's electronegativity, right. That's how strongly one atom in a compound pulls the electron cloud towards it. So this is, how willing your cousin Joey is to share the blankets or wrap them all around, and roll over and take them all. So we can look at electronegativities and we can predict what kind of bond is going to form. If you would be so kind as to go to page 151 in your book. Okay, do you remember what the most electronegative thing that exists is? Fluorine. Has an assigned electronegativity of 4. If we take the most electronegative thing that exists and we attempt to bond it to the least electronegative thing that exists, which is francium, the difference in electronegativities is 3.3. If we have a difference of 3.3, this is something that is 100% ionic, purely ionic. So at one end we have 1.3. If you have two identical atoms, like a molecule of chlorine and a molecule of chlorine, what's their electronegativity difference? 0. They're identical. They have the same desire for electrons. So they have a difference of 0, and that's going to be purely covalent. Everything else, oh, I'm sorry, I wrote 3.3, 1.3, that's 3.3. Everything else is on this spectrum. So as we go from 0 to, we consider up to 0.3 to be purely covalent. From 0.3 to 1.7 is considered a polar covalent. And everything up here is ionic. Let's actually put that on a graphic, because we have a graphic for that. Okay, so here's our graphic, and here's our 0.3, 1.7, Gesundheit. So in this area between 0 and 0.3, very, very little difference in electronegativity. We consider these to be non-polar covalent bonds. Basically, there are two types of covalent bonds. There are non-polar and polar. We're going to talk a lot about those today. If we're between 0.3 and 1.7, that's a polar covalent bond. And anything above 1.7, that is a significant enough difference in electronegativity that one atom is going to execute a grab. One atom is just going to completely take the electrons, and the other one is going to completely give them up. So let's practice identifying some pairs. Let's look at some pairs and predict how they're going to bond. Okay, so we figured out our EN difference. We have electronegativity of 0.9 and an electronegativity of 3. Subtracting them, we get an EN difference of 2.1. Where does that put us on here? Which area does that put us into? Yeah, these two form an ionic bond. Okay, so sodium and chloride form an ionic bond. Well, let's look at iron and oxygen. What is the electronegativity of iron? 1.8. What's the electronegativity of oxygen? 3.5. So 3.5 minus 1.8. 1.7. What's that going to be? Pardon? It's on the border, and it actually it does actually form an ionic bond, but it's really close to being polar covalent. But it actually, experimentally, we know it does form an ionic bond. Okay. What about N and O? Nitrogen and oxygen. So what is nitrogen's electronegativity? 3.0, and oxygen is 3.5. So we have an EN difference of 0.5. What kind of bond is that? It's covalent. Which kind of covalent? Let's go back to our chart here. Which is it? Polar. Yeah. It's a polar covalent bond. Now let me caution you. A word of caution here. This is one of the pitfalls of doing this. Somebody at some point will tell me, oh yeah, well the electronegativity is 0.5 for that compound. No! It's not. The electronegativity difference between those two substances is 0.5, but the 0.5 is nobody's electronegativity. Nope, nope, nope. Nitrogen has a 3, oxygen has a 3.5. This is the electronegativity difference. So do not tell me, oh yeah, sodium chloride's got a 2.1 electronegativity. No, it doesn't. That's the difference in the two electronegativities. Compounds do not have their own electronegativities. Only individual substances have an electronegativity, so an element has an electronegativity. Between two elements, we can find the difference in the electronegativity. It seems like a subtle distinction, but it's important. Okay, so I'm going to let you practice a couple on your own. I give to you calcium and fluoride. I give to you silver and form. They have an EN difference of 3. Nicely worded, ma'am. EN difference of 3, which means it's going to be what kind of bond? Ionic. And you will find that typically group 1 and 2 form ionic bonds with group 17. That's pretty common. Okay, what about rubidium and oxygen? So here we have a transition metal and oxygen. What's the electronegativity difference? 1.3, which makes it what? Makes it a polar covalent bond. And what about carbon and oxygen? EN difference of 1, which makes it polar covalent. Okay, now, I'm going to give you one real quick to do without looking at anything. Close your books. Chlorine and chlorine, what's the electronegativity difference? 0. What kind of bond is this? Purely covalent. Yeah, they are sharing perfectly 100% evenly. Okay, so I would like to talk about my friend Mickey. We'll talk a lot about Mickey in here. M-I-C-K-E-Y-M-O-U-S-E. It's water. So, water just happens to have this weird shape. It looks like a Mickey Mouse. So we talk a lot about Mickey. We got 1 oxygen. We got 2 hydrogens. Hey, look there. It's a mouse. Look at the electronegativity difference between hydrogen and oxygen, if you would be so kind. Okay, so we have an EN difference of 1.4. What kind of bond does that make it? Polar covalent. Pretty, and pretty seriously polar covalent. If it was above 1.7, it would be an ionic bond. So oxygen, which is the more electronegative one in here? Which is the higher electronegativity? The oxygen. In other words, oxygen is your cousin Joey. Oxygen is the blanket hog. Oxygen is pulling the electron cloud over to itself. So what this looks like, let's actually use a simplified model of this to start with. If we have substance A and substance B, and they are sharing their electron cloud perfectly evenly, they're going to look like this, right? This is 0 electronegativity difference. However, if A and B aren't sharing evenly and they have a big electronegativity difference, it's going to end up looking more like this. It's like a bowling pin turned on its side. Because A, also known as your cousin Joey the blanket hog, has sucked all of the electron cloud over to itself. Well, Now if we go back and look at Mickey, which one is more electronegative? Which one? Oxygen. So what happens, we'll actually take Mickey over to a new page. What happens is that rather than looking like this, with a well-proportioned little face with a nice balanced face and ears, Mickey ends up with these little skinny ears and this big double chin. So Mickey has got wattles. Mickey has like a triple chin. Mickey's got a bunch of electron cloud hanging down around the oxygen. Well, let's think about bromine and bromine. Okay? They have a bromance. They do, it's true. They're never seen alone. You know, if you see one bromine, you see another bromine. They form a diatomic molecule. So what's their electronegativity difference? 0. They're identical. Duh. So they are sharing this cloud evenly. What that means is that at any given point on a bromine molecule, whether it's here, or here, or here, or here, or here, or any place you want to pick, it's neutral. Because every single place is experiencing an equal influence from the positive nucleus and that negative electron cloud. So it is completely 100% balanced overall. Totally neutral. No areas of partial charge. Okay? It's hard to read. I lost my stylus. I apologize. So that's not the case with Mickey. So the oxygen has got a lot of electron cloud around it, a lot of cotton candy down around that oxygen. The electron cloud would have what charge? What's the charge of an electron? Negative. The electron cloud is a heavy negative charge. Well, up here where these hydrogen are, there's very little electron cloud around the hydrogen, right? What's a hydrogen without its electron? A naked proton. Remember the little naked toddler running up the street with a plus sign on her belly? Not that I did that to my daughter this Halloween. But it's a naked proton. It's got a positive charge. So Mickey's ears end up being areas of positive charge. We should actually move this outside there. Now, overall, is water still neutral? Yes, it is. It is a neutral molecule. However, on a water molecule, there are areas of, we call it partial charge. We call it partial charge, and I can't write it there. Okay. That's because it's a polar covalent bond. They're not sharing evenly. So anything that is bonded in a polar covalent fashion is going to have these areas of partial charge. Polar covalent molecules have areas of positive and negative charge on the ends. If it's nonpolar, everything is shared evenly. There are no areas of charge. Everything is neutral. Okay? Okay, so let's go back to our little example of Mickey. Wait, hold on. Why do we care? We don't? Well, if it doesn't change the way they behave, we wouldn't, right? If it doesn't change how they act chemically, then it doesn't matter. But it turns out it does. So let's take our Mickey here. Oh, Mickey, you're so fine, you're so fine. You blow my mind. Hey, Mickey. Hey, water. Okay. Let's clear that. So if we line up a bunch of water molecules, like in a glass, What's going to happen? Are they going to go any which way? Oh, no, they're not. No, no, they are not. All those Mickeys are going to line up in a very particular fashion. Why? Yeah, because there are areas of charge on them. And all those little positive ears are attracted to all those little negative chins. And so polar molecules actually behave in a different way than nonpolar molecules. When we get into talking about solutions and solvents, you will find that polar substances tend to be really good solvents. There are a lot of things that are not soluble in oil. Oil is nonpolar. Water is polar. And so it dissolves a lot of things really, really well as a result. So if you put a bunch of bromines, you could put a bunch of bromines together. Do they have any particular order in which they're going to line up? No. Totally, it doesn't matter. Doesn't matter at all. They're going to fill in random, completely random fashion because they don't have any areas of partial charge. They are neutral overall. And so they can go anywhere they darn well please. And they do. Okay? So nonpolar behave differently than polar. And one of the, well, we talked yesterday about how some things are soluble in gasoline that are not soluble in water. Grease is nonpolar. So is gasoline. They tend to dissolve one another very nicely. Water is polar. Polar stuff tends to dissolve a lot of things, but nonpolars and nonpolars tend to dissolve one another. Okay, let's talk a little bit about molecules. Okay, so we've got hydrogen and oxygen. They form water. We said that they are polarly covalently bound. Whenever we have something that is held with any kind of covalent bonds, it forms a molecule. So a molecule, by definition, is a group of atoms that are held together with covalent bonds, and they're neutral overall. Now, water's got those areas of partial charge, but it is neutral overall. So if we have chlorine, that's purely covalent, neutral overall, forms a molecule. So anytime you've got a group of atoms that are held together covalently, they're sharing electrons, and they're neutral overall, that is a molecule. We will talk about things that are held together with covalent bonds that are not neutral, which are not molecules. We're getting there. If something is held together with covalent bonds, it's got molecules, and it's called a molecular compound. Now, molecular compounds behave differently than ionic compounds. In the lab that we're going to do probably on Thursday, you'll examine some of those differences. You'll be doing some testing. What about NaCl? What kind of bonds did we say held that together? Is I think electronegativity difference of 2 something? It's ionic. Can you have a molecule of salt? No, you cannot. There are no molecules of salt. There are no molecules of sodium fluoride. There are no molecules of potassium bromide. There are no molecules of calcium chloride. Those are all ionic compounds. If it's an ionic compound, no molecules. So if I ever ask you, like, how many molecules of salt, blah, 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 it's a trick question. I'm being mean. Would I do that? Yes. Yes, I would. Yes, ma'am. So there are no molecules of anything that's held together with ionic bonds. If you've got covalent bonds, whether they're polar or nonpolar, you got a molecule. So when we start into naming, which is in the next chapter, when we start talking about chemical naming, for a molecular compound and only for a molecular compound, that formula is a literal exact number of atoms of each kind. So when we talk about H2O, Oh, in every molecule of water there are 2 hydrogens and 1 oxygen. When we talk about C6H12O6, in every single molecule of glucose there are 6 carbons, 12 hydrogens, 6 oxygens. It is a literal, exact representation of what's in the molecule. That is not true for ionic compounds. We'll get into that a little bit later in this chapter. But for molecular compounds only, this is a literal truth. It is literally made up of 6 carbons. Not 3, not 12, 6 carbons, period. We also have the diatomic molecules. We have things like O2 and Cl2 and N2. That is literally 2 oxygens bound together, 2 chlorines bound together. So that's only true for molecular compounds, though. Tell you what, I'm going to break the video here so it's not too long.